Dear learners, good morning to all. I welcome you all in this module. Today, we will discuss about the characteristics of wind energy and the different tools available for the analysis of the behavior of wind characteristics. After learning this module, you all will be able to identify suitable location for wind energy projects based on wind speed, direction and other site specific factors. You all will be able to evaluate the economic viability of wind energy projects. You will be able to determine the expected energy output and revenue generation over the project's lifetime. You will be able to identify the size and design of turbine for a particular location. You will be also able to use wind data and simulation tool to predict the energy production of wind turbine over different time frames. So, we will start with the wind characteristics. Basically, wind characteristics refers to the property and behavior of the wind as it flows through the atmosphere. These characteristics plays a crucial role in determining the feasibility and efficiency of wind energy generation. Understanding these wind characteristics help us in selecting suitable locations for wind farms, designing efficient wind turbines and optimizing the energy production. Now, let us discuss the important wind characteristics one by one. First, one of the major and important wind characteristics is the speed of wind, or we can say wind speed. Wind speed is a measurement of the velocity at which the air is moving in the atmosphere. It is a fundamental parameter used to characterize the intensity of wind at a specific location and at a specific time. Wind speed is an important factor in various applications including meteorology, aviation and most particularly in wind energy generation. It is typically measured in meter per second. It varies widely over different time scale. It can change rapidly due to weather conditions, time of the day and due to geographic feature. Wind speed is influenced by factors like pressure gradients, temperature difference, terrain features and local geographic condition. For wind energy applications, areas with consistent and high wind speed are preferred for efficient energy generation. Wind speed is a primary factor influencing the amount of energy that can be captured from the wind by the help of wind turbines. Wind turbines typically have a minimum wind speed which is called a cut-in wind speed. A cut-in wind speed is a speed at which turbine start generating power. It also has a rated wind speed. The rated wind speed is a speed at which the turbine produce their maximum rated power. Above a certain wind speed, we call a cutout wind speed for the wind turbine. The cutout wind speed is a speed at which the turbine may shut down to avoid damage from excessive forces. The accurate and reliable wind speed data is very essential for planning and operating wind energy system effectively and safely. After wind speed, we collect or record another wind characteristics which is called wind direction. It indicates the compass direction from which the wind is coming. It is typically measured in degree clockwise from the north. Wind direction is critical for aligning wind turbine arrays to face the prevailing wind to maximizing energy capture. It is represented graphically with the help of wind rows. Wind rows displays the frequency and distribution of wind direction at a specific location over a given time period. Wind roses provide valuable information about prevailing wind patterns, which is useful for various applications, including urban planning, agriculture, and wind energy site selection. Wind direction is a critical factor in the placement and orientation of wind turbine in wind farms. Turbines are typically positioned so that they faces the prevailing wind direction in order to maximize the energy capture. Terrain features such as mountains and valley can influence local wind pattern and can cause the changes in wind direction. Understanding wind direction contributes to the safety, efficiency, and effective decision making in wind energy production. Third important wind characteristic is wind shear. Wind shear is a change in wind speed and direction over a short distance in the atmosphere, typically in vertical direction. It can occur at various heights and is often associated with changes in weather patterns, topography, and atmospheric condition. There are two types of wind shear: horizontal and vertical wind shear. Wind shear affects the performance of wind turbines. Turbulence caused by wind shear create uneven loading on the wind turbine blades, leading to increase in wear and fatigue. Wind shear can also lead to wake effect, where downstream turbines experience lower wind speeds due to the turbulence created by upstream turbines. Now, here we have came across one more important characteristics, that is known as turbulence. Turbulence is an irregular fluctuation in wind speed and direction caused by the factor like terrain, building, and atmospheric condition. Turbulence affects the load distribution on wind turbine and can contribute to wear and fatigue. Turbulence disrupts the smooth airflow over the blades, hence reducing their efficiency in capturing wind energy. This phenomena is often called as turbine aerodynamic performance degradation. This reduced efficiency can lead to the lower power output and decreased overall energy generation. Wind duration is also an important characteristics. Wind duration refers to the length of time during which a certain wind speed or a range of wind speed is sustained. Longer duration of strong wind and consistent wind are ideal for wind energy generation. Wind duration is used in frequency analysis to determine the probability of specific wind speeds occurring over different time periods. This analysis helps in assessing the wind energy potential of a site and designing wind energy systems. Wind duration is a factor in estimating the energy production of wind turbine. It is used to calculate the amount of energy generated at different wind speed and the corresponding duration. Wind duration data is crucial for assessing the wind resource potential of a site for potential wind energy project. It helps to determine the consistency and reliability of wind conditions over a period of time. Another wind characteristics is frequency distribution. Wind speed frequency distribution represent how often different wind speed occurs over a specific period at a particular location. Understanding frequency distribution helps us to predict the energy output of wind turbine over time. The collected wind speed data is analyzed to create a frequency distribution. The data is characterized into a bins or intervals of a wind speed range. The frequency distribution is visualized in terms of histogram with wind speed on the x axis and frequency of occurrence on y axis. The shape of frequency distribution curve provide insights into the prevailing wind pattern at the location. For example, a higher peak in the curve indicates a more common wind speed range. It provides a quantitative and statistical basis for evaluating the reliability, variability and energy production potential of wind resource at specific location. One of the most common distribution is Weibull distribution, which is used in a wind energy sector. It is a probability distribution which is used in the field of wind energy to model the frequency distribution of wind speed at a specific location and at a specific height. It provides a statistical representation of how wind speed varies over time, which is essential for assessing the wind energy potential of a site, designing wind turbines and optimizing operational strategies. Weibull distribution is particularly well suited for modeling wind speed frequency distribution because of its flexibility and ability to fit a wide range of wind data. Key characteristics of Weibull distribution are shape parameter and scale parameter. First, we will discuss shape parameter. The shape parameter of Weibull distribution determines the shape of the distribution curve. A lower shape parameter results in a broader distribution with lower wind speeds being more frequent, while a higher shape parameter lead to a narrow distribution with higher wind speeds being more frequent. Second parameter is a scale parameter and it is represented by C. The scale parameter of Weibull distribution represents the wind speed at which the probability density function reaches its maximum value. It provides an indication of the typical wind speed at the site. The Weibull distribution is used to estimate the expected energy production of a wind turbine or a wind farm at a specific location for a specific height. By integrating the product of wind speed and power curve over the distribution, the average annual energy output can be calculated. Now, we may discuss wind power density. It is the amount of energy available in the wind per unit area. It is an important factor for assessing the energy potential of a site and designing efficient turbine. The mathematical formula to calculate wind power density can be found below. It can be calculated by the multiplying 1 by 2 into density of air multiplied by the cube of wind speed. The another characteristics is annual energy production. Annual energy production is the total amount of electrical energy generated by a wind turbine or a wind farm over the period of a year. It is a key metric which is used to evaluate the performance and economic viability of a wind energy project. Annual energy production takes into account factors such as wind resource at the location, the efficiency of wind turbine and any downtime or maintenance period. The formula to calculate annual energy production can be written as wind power density multiplied by area multiplied by capacity factor multiplied by total hours in a area. Here in this formula, the capacity factor represents the efficiency of the wind turbine in converting the available wind energy into electricity. It is the ratio of actual energy output to the maximum possible output if the turbine is operated at its rated capacity continuously. The hours in a year here can be found as number of hours in a year. Typically, it is taken as 8,760 hours in a year. Another wind characteristics is tip speed ratio, which is acronym as TSR. It is used to describe the performance and efficiency of a wind turbine. It is a dimensionless ratio that compares the speed of the tip of wind turbine blade to the speed of the wind. The tip speed ratio helps in determining the optimal rotational speed of the wind turbine for maximum energy capture. The mathematical formula to calculate tip speed ratio is blade tip speed divided by wind speed. Here the blade tip speed is the linear speed at which the tip of wind turbine is moving. It can be calculated as the product of blade's length and the rotational speed of the rotor. Wind speed here is the velocity of wind. Another wind characteristics is gustiness. Gusts are generally and are rapid and temporary increase in wind speed. Gustiness can be caused by weather phenomena like change in atmospheric stability. All the wind turbine must be designed to withstand gust without compromising their structural integrity for their safe performance. Another wind characteristics is seasonal and annual wind patterns. Wind patterns plays a very important role while developing a wind energy project. Wind pattern can vary across different seasons of the year due to change in atmospheric condition and the pressure. In many regions, winter wind tend to be stronger and more consistent due to increased temperature gradients between the land and sea. Cold air from polar region can lead to more frequent low pressure system and stronger winds. Summer winds are often influenced by temperature difference between land and sea. Coastal areas may experience onshore wind due to temperature variation. In some region, summer wind can be relatively calm due to high pressure system and stable atmospheric condition. Annual wind pattern consider the wind behavior over the entire year, including all season. Analyzing annual patterns helps in understanding the long-term wind resource potential. Analyzing both seasonal and annual wind pattern is essential for comprehensive assessment of wind resource and effective project management. It allows stakeholders to design and operate wind farm that align with the prevailing climatic condition, maximizing energy production and long-term project success. To analyze all the above wind characteristics discussed above, we require different wind energy simulation tools. Simulation tools are used to analyze the wind characteristics associated with historical wind data and create wind resource map to access the potential energy output of a specific site. This information is crucial for determining the viability of establishing a wind farm at a particular location. Simulation tool helps engineers to design and optimize wind turbine components for maximum efficiency and durability. These simulation tools simulate the aerodynamic behavior of the turbine blades, the mechanical dynamics of component like the gearbox and generator, and it also enhances the overall performance of the turbine. Computational fluid dynamics simulation are used to study the airflow around wind turbine blades and other components. It helps in optimizing the shape of blade for better energy capture and reducing aerodynamic losses. Simulation tool model the structural behavior of wind turbine component under various load, including wind, gravity and mechanical forces. This ensures that the component are designed to withstand the stresses they will encounter over their operational lifetime. Wind turbine uses advanced control system to optimize power production and to respond against changing wind condition. Nowadays, simulation tools are used to develop, test and fine tune the control algorithm before implementing it in real turbines. Wind farms need to be integrated into the electrical grid to ensure stable and reliable power delivery. Simulation tools are used to study the interaction between wind farm and the grid, including power quality, voltage stability and grid behavior during various scenarios. Simulation tool can model the potential environmental impacts of wind farm, including noise levels, shadow flickers and bird collision risk. This all information is important for obtaining permits and addressing environmental concern. Therefore, simulation tools are used for all these purposes. Simulation tools are also used for educational purposes to train engineers, researchers and technicians working in the field of wind energy technologies and performing different operations. They provide a platform for hands-on learning without the need of a physical prototype. The simulation tools can be used to practice by using our own hands without using the physical prototypes. Financial and economic analysis is also done with the help of a simulation tool. Simulation tool combined with financial models helps in assessing the economic feasibility of wind energy projects. By using simulation tools, we can estimate the expected energy production, its operational cost and revenue generation over the project lifetimes. We can also use simulation tools for maintenance and conditioning monitoring. In order to predict maintenance, and simulation tool can be used to predict maintenance need and assess the health of wind turbine components. This helps in planning maintenance activities and avoiding unexpected downtime. So, it is very essential that one should keep in mind that the popularity of a specific tool can change over time. So, it is a good idea to check for the latest information available for simulation tool. Some of the widely used simulation tool in the wind energy sector includes WASP, WindPro, WindSim, etc. Let us discuss one by one here. First, the most common simulation tools used in wind energy sector is WASP. Its full form is Wind Atlas Analysis and Application Program. It is a widely used software for wind resource assessment. It helps in analyzing wind data to determine the wind energy potential of a particular site. It is used by wind developers to estimate the expected energy output from a wind farm. Basically, WASP uses a Gaussian model to simulate the wind flow based on the input data. It runs the model to calculate the wind flow at various height and locations across the site. The major focus one should keep in mind or one should focus is how to use a WASP. So, using WASP involves several steps to assess the wind resource potential of a particular site. First, gather historical wind data for the particular site. This should include wind speed and wind direction measurement from the meteorological station. Second, collect information about the site's terrain, obstacle and other relevant geographical features. Third, we must give the input in terms of geographical coordinates of our site. Then we need to specify the height of the measurement from where or from which we have collected the wind data. Further, after providing the height, we have to import or create a digital elevation model of the terrain. This digital elevation model provide information about the topography and elevation of the site. Once we have created digital elevation model, then we need to define obstacles available nearby wind farm. The obstacles here we may define such as buildings, trees and other structure that may affect the wind flow. After defining the obstacles, we have to define the roughness of the terrain. The roughness describes how smooth or rough the land surface is, which may influence wind speed and turbine. At last, it gives the result, and as an engineer or researcher or an academician, we need to analyze the result and interpret the result. The second most common simulation software or tool which is available at wind energy sector is WindPro. WindPro is a software used for designing wind farm, used for site assessment and used for estimation of energy production. It combines wind resource data with the specification of turbine to provide insight of the project feasibility and optimization. In order to run or in order to operate the WindPro, first we need to download it and install the WindPro in our workstation or a laptop in which you are working, which may need a license or a subscription to access the full feature of this software. After installation, we need to launch WindPro and we need to create a new project for our wind energy assessment. Once the software is launched and the project has been created, we need to import or create a digital elevation model as similar to the WASP. This data helps in assessing the wind flow over the landscape. Then we need to give input in terms of meteorological data which is available from the meteorological mast or any which is available from the meteorological mast, which include wind speed, wind direction, humidity, temperature and pressure. All this data should be available at a particular height. This data is crucial for wind resource assessment, including wind speed and direction at a various height. Once the input has been defined in terms of meteorological data, we need to define the turbine specification. That means we need to give the input specification of the wind turbine which we plan to use for a particular wind site and for a particular height. This input specification include parameters like rotor diameter, hub height, power curve and more. Once the meteorological input has been given, turbine specification has been uploaded, then we need to create a wind farm layout by using WindPro tools. We use WindPro tools to design the layout of our wind farm. We need to place the turbine on the terrain based on the factor like wind direction, turbine spacing and terrain characteristics. WindPro provide visualization tools to help us see how the turbine will be placed on the site. Then once all types of input has been given, we need to run the module of energy production. Then we need to use the module calculate. While using calculate, WindPro energy production module will estimate the potential energy output of the wind farm which has been designed in WindPro. The software uses the wind data and turbine specification to simulate the wind energy production over a specified period of time. The WindPro can provide a detailed report and graphs showing the expected energy production, capacity factor and other performance metrics. Once we get the result, we examine the energy production and understand how different turbine positions and layout impacts the energy generation. The third simulation tool which is used in wind energy sector is OpenFast. OpenFast is an open source engineering simulation tool which has been developed by National Renewable Energy Laboratory. It is designed for the detailed analysis of wind turbine, which may include both aerodynamic and structural dynamics. It is commonly used for the design of turbine and to evaluate the performance of the turbine.